Hello friends, how are you all doing today? Today I am out. My friend has a farm out in for sales. It's called Salad Days Farm. And I have come out to enjoy the beautiful weather and do a little work, and that way I'm not sitting in my house alone, right? So I am going to help them do some work momentarily. So I thought I would bring you out to the farm. Woo! Okay, anyway, buy local, right? Okay, so I'm going to continue on with what we were talking about yesterday. I recorded a video on measures of central tendency, and so today we are going to continue on and talk about measures of spread. This is working. Hello. Okay. So whenever we're thinking about measures of spread, we're thinking about how much our data points are spread about the mean. So any set of data that we collect is going to have a mean associated with it. And that mean we are going to assume is where most of the scores are going to be hovering around. Now, this is just an assumption that we make. This is something we think about when we think about the mean of the data. Now, we were talking about in ways that the mean is not necessarily representative of the data, and our measures of spread are going to tell us how much the mean actually represents our data. How representative is it of the data? So I think the best example of this is to talk about a test score. So whenever you have a class of students and they take an exam, this is something you guys are all familiar with, there is going to be a mean associated with that test grade. Well, as you can probably assume, those people that scored really high and those people that scored, especially the people that score really low, if you get a couple people in the class that are scoring in the 40s, that's really going to pull that average down. So whenever you have your class of students and you're looking at a test grade, let's say the test grade, the mean is 65, you want to know just how representative is that number for the class. Did most people in the class get 65s, or was it just a few students that really pulled that average down? And so you can look at the spread of that data. The way we do this whenever we're thinking about statistics and we're thinking about the mean is through the standard deviation. So the standard deviation is our value that tells us just how much our data points vary about the mean. And we don't really get into calculations in this class. Whenever we get into the ANOVA tests, I will talk a little bit more about specific calculations, but we have computer programs, fortunately. Download SPSS. We have computer programs that do this for us, so we actually do not have to do any calculations by hand. So you do not need to calculate standard deviation. But the way standard deviation works is that this is our value to tell us just how spread our data is. Whenever we have high standard deviations, this is going to represent that our data points are not really clustered around the mean. They're kind of all over the place, but lower standard deviations suggest that the mean is representative of our data, that most of our data points do hover around that mean. If you had a classroom of 100 students and they all scored a 65 on the test, then your standard deviation would be 0. So if we have no variation in the data, we're going to get 0 on our standard deviation. Okay, so that brings me to the standard bell curve. This is something that I am hopeful that you all are familiar with. So here you can see these values. You can see mu, which is this down here. This right here, this value represents the population mean, and then over here our sigmas represent the population standard deviation. So this here is what we call a standard normal curve. This is the bell curve. And we assume that this is how this works in the population. So I think that the best example of this is to talk about IQ scores. IQ scores do tend to follow the standard bell curve. So here we have our mean here in the middle. And if we were to put IQ onto this, then we would have a 100 right here where we have the mu sign. We would have a 100 right there. 100 is the average IQ score. And within one standard deviation of the of 100, which would be 90 to 110, you're going to capture about 70% of the population. So 70%, give or take, of the population is going to have an IQ score somewhere between 90 and 110. Then whenever you get 2 standard deviations out, you get your less common scores. So there you're going to capture another, say, 14% on one side and 14% on the other. So another 28% of the population is going to be in that 80 to 120. So what that is really saying is that roughly 95% of the population in the world, right, if they were to take an IQ score, is going to have an IQ score somewhere between 80 and 120. And that's going to represent 95% of the population. So then we have these tails out here, which is 3 standard deviations away. And this is going to represent a 2.5% on one tail and 2.5% on the other tail. So 5% of the population out there is going to score on those tail ends. It's important to note that using this, that it's just as likely for someone to have an IQ score of over 130 as it is for somebody to have an IQ score of less than 70. Okay, so as I'm talking about the population, and I'm talking about the population standard deviations and the population mean, one thing to remember is this picture that I've already shown you all quite a bit in class. And what this is telling you is that, remember what we are doing when we run our experiments is that we have our population that we're interested in, our population of interest. Again, whether it's like college students, or it could be women, or it could be Americans, or it could be any sort of group that you're interested in, you have a population that you are trying to learn something about. And so we pull our participants from that population and we put them into our groups. And then we're going to pull some data on them. We're going to do some magical calculations, and we are going to infer something about that. And we are going to infer that if we were to poll every single person in the population, in our population of interest, that that's the value that we would get. So again, if we have people in our experimental group and 80% of them had an increase in locomotor activity when they took cocaine, then that would suggest that if we were to give everybody in the population cocaine, that 80% of them would have an increase in locomotor activity. So here's a little bit of statistical jargon as we start thinking about these values. So there is a value out there in the population. There is a measurement. If we were to poll every single person in our population of interest, there's going to be a number out there. There's going to be a mean. So there is a real true value out there. Will we ever find it? Of course not. We can never do this, right? But there is a true value out there. So this is a precise measurement. This is the parameter of the population. This is a numerical characteristic of the population, and there is something out there. There's no way we could ever do that. So that's why we use statistics. So remember that statistics is just an estimate. This is just a guess. We are just inferring that what we're going to see in our sample is what we're also going to see in the population. So this is an estimate, and this is not a precise value. So whenever we're looking at these, you're going to have 2 different measures, and standard deviation is our standard measure of spread. And this is, again, this is a descriptive method. This describes our data. It tells us information about how much our values are spread about the mean. So this is going to tell us about our sample and how much our sample is spread about its mean. The value that you guys are going to be reporting in your statistical exercises that we're going to be doing is the standard error of the mean. This is what you're going to most likely see. This is the thing that's most likely reported out. And this is represented by SEM there, as you can see on the slide. And this is just an estimate of how far your mean in your data is from the population mean. And it's just a guess because we could never know what the population mean is. So it's just a guess of what we think, how far we think your mean is from the true parameter out there. So standard deviation, the standard error of the mean is the standard deviation of your sample mean. That's one way you can think about it. Okay, so that brings me to the standard Z distribution. This is probably something that you've heard of. A Z distribution is representative of the population. This is a standard normal curve. It's called a Z distribution because in a Z distribution, the mean is 0 and the standard deviation is 1. Okay, so as we move further into statistics, each test has its own distribution that it uses. So the Z distribution is one distribution, and it is our standard normal distribution. However, depending on how we have our experiments set up, we're going to have multiple or maybe just one independent variable. We could have multiple independent variables. We could have 2 levels. We could have multiple levels. So it depends on what we're doing, what type of test we are going to look at. So whenever we have our most simple design, our single factor 2-level designs, we can use a t-test, which is going to use a t-distribution. A t-distribution is different. It makes different assumptions about the data. And so it's going to be similar to a z-distribution, but it does have its own characteristics that we're looking at because of the assumptions that we're making about our sample. Same thing with the ANOVA. In an ANOVA test, we're going to have multiple independent variables here. This is what we use to test our factorial designs. This is what we use to test multi-level designs. So this is going to use what's known as an F distribution. And it's a variation, again, on the Z distribution because we have to make different assumptions because we have so many independent variables or because we have so many levels. So we're going to have to make different assumptions. And so these distributions are different from the Z distribution. And these are the ones that we're using whenever we are testing. So it's important to think about the critical value. You probably, whenever you guys took Math 130 and were taking stats, you had one of those charts where you had the critical values. Each one of these tests has a different critical value and makes different assumptions about our data. Okay, so I'm going to stop there, and I hope you guys enjoyed this video. And again, I am going to be online tomorrow during our class time on Slack for you guys to ask me questions if you have questions to ask. Thank you. I hope you guys are enjoying this beautiful day.